Welcome back, everyone. Happy Wednesday, hump day, middle of the week. You can get through it. We are in topic 2.2. We're looking at periodic table trends. We now know all about electron configurations, how to figure out where electrons are, and now we're going to see how that informs trends across the periodic table. The periodic table is a work of art. It is a masterful piece of science, and it caused a revolution in our understanding of matter. That all the stuff around us has protons, electrons, and it's because of these protons and electrons that we have so many different types of matter with different atomic radii, different properties, different reactivities. When we understand how to use and interpret our periodic table, we can understand a lot about the stuff, the matter around us, and do important things with that. So as a little reminder, make sure you're working through those practice problems. We're done topic 2.1, so that means you need to be working through those problems. Hopefully you're done them already. If not, by the end of this week, make sure you're up to date on those practice problems. We realize the Lab 1 rotation is happening this week, but not next week. But it is the week following. So that means we won't have questions on Lab 1 on the test because only half of our students will have done it by test 1. Okay, we're going to jump right in today. We're starting now with atomic size, figuring out how large or small an atom is and how this is related to bond length. So when we try to figure out how big an atom is, well, all atoms are really, really small. Notice the PM, we're in picometer territory, really itty bitty. Most of the atom, or the dense core of the atom, I should say, is made up of the protons and the neutrons, and it is very tiny. And then we have this electron cloud around the nucleus. And we know it's not just some willy-nilly cloud. These electrons have different wave functions. They're in s orbitals, p orbitals, d orbitals, and so on. Figuring out how big these atoms are with these electrons that are doing all sorts of cool things could be challenging. But scientists have come up with some really cool ways to figure out and have a pretty good idea of atomic size. To be able to do this, we have to see how an atom interacts with another atom. So, for example, bromine, Br2, one atom of bromine interacting with another atom of bromine. We can measure the distance between those two nuclei using X-ray crystallography. Beyond the scope of our course, but you can use cool energy and see the diffraction patterns and how far apart these nuclei are. So we could come up with a covalent radius for bromine by saying, okay, using X-ray crystallography, we can figure out and approximate the length between these two nuclei, so the bond length, divide that by 2, and that would be the radius of one of the atoms. So that would be the covalent radius. Well, not all materials form covalent bonds. If we have a metal, then they're just kind of hanging out side by side, and then we could measure the metallic radius. Again, the distance between the two nuclei, divide it by 2, and that gives us the radius, an estimation of the size of the atom. We're going to see later today that ions, cations, anions, have very different sizes compared to the atom that's not charged. But again, we can still estimate the atomic radius, how large or small it is, often by comparing to an oxide radius. That's something that we know, and we can measure bigger or smaller from there. The end result is that we can have an estimate and a good idea of the atomic radii, how large or small an atom is. Which brings us to this really cool picture that you have in your workbook. Now, this picture doesn't show all the elements on the periodic table. It's showing group 1 and 2, so our S block, and then it's showing part of the P block. So we have some of the main group elements in this picture here, not all of them. But we have a little snapshot that's going to let us have a good understanding of the trends. Today, we're going to talk about a number of different trends using our periodic table, where we can predict properties of an atom because of where it's placed on the periodic table. We need to know these trends, but it's going to be helpful if we understand why these trends exist. So you need to, well, I'm not even going to say you need to memorize them. You need to know them, but rather than blunt force memorizing them, you come up with the rationale, the reason for these trends, and that's going to help you out. So when we look at this image here, we can see that as we go from the top of the periodic table, from period 1 to down to the bottom, the atomic radius is increasing. Now, last class I asked you how many of you study music. Many of you have. This kind of looks like a sideways crescendo or decrescendo, depending on which way you're going. But we can see as we go from the top to the bottom, the atomic radii are getting larger. And this probably, hopefully, makes intuitive sense. If we think about the valence electrons in each of these atoms, hydrogen here has its valence electrons in 1s orbitals, lithium, 2s, sodium, 3s, and as we go out, or as we go down the periodic table, the valence electrons are in orbitals that have a higher principal quantum number. So 1s, 2s, 3s, 4s, 5s. So it makes sense as we go down the periodic table, the size is increasing. Now, what might not make as intuitive sense is that as we go across the periodic table, the size is getting smaller. When we look in one period, so one row of the periodic table, as we go across, they're getting smaller. I don't think this is intuitive because as we go across, we're adding more electrons. When we go from sodium to magnesium, for neutral atoms, magnesium has another electron. We've added another electron, but it actually got smaller. And as we go across to group 3 and 4 and 5 and 17, 18, they keep getting smaller. Reason for that is effective nuclear charge. Remember last class, we spent a lot of time talking about that Z star, where it's a measure of the attraction to the nucleus that those valence electrons experience. So we have the protons in the nucleus, we have the core electrons shielding those protons, and then we have the valence electrons. Group 1 elements on our periodic table have an effective nuclear charge of +1. They're being pulled in with an effective nuclear charge of +1. But as we go across the periodic table to the next group, it gets pulled in a little more because the effective nuclear charge is now +2, +3, +4. And as we get all the way to the noble gases, it's like +8. The effective nuclear charge has increased. Even though we've added electrons as we go across a row, we're also adding protons. We're not changing the number of core electrons, we're just increasing the number of valence. The effective nuclear charge increases, those electrons are pulled in even tighter, and the atomic radii decreases. Okay, so that's our atomic radii, looking at like the cartoon version of these sizes as they get smaller or larger as we move across the periodic table. Well, this is another way to visualize and compare the atomic radii across the periodic table. So first, let's orient ourselves to this really cool graph. So on the bottom, along the x-axis, we have the atomic number. So that's our Z, that's the number of protons. And we know as we go across the periodic table and then down to the next row, the number of protons or atomic number is increasing. Along our y-axis, we have atomic radius. And again, we're in really tiny size, like picometers. We can't see this with our eye. We can't even see it with most of our microscopes. It's really tiny. Now let's walk our way across this graph. Let's start with helium. It has its valence electrons in the 1s orbital, pretty tiny. But then we jump down to the next period and we get to lithium. Lithium on our periodic table has its valence electrons in the 2s orbital. Its valence electrons are 1 electron in the 2s. Then, as we go across the periodic table, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, the effective nuclear charge is increasing and the atomic size is decreasing. As we fill up the 2s and the 2p orbitals, we can see the radius is decreasing as we go across the periodic table. And then we hit the noble gas neon. We've filled up the 2s and the 2p. Well, then we add another proton, we add another electron, and we're now in 3s1 territory. The extra electron is added to the higher principal quantum number. Sodium is a whole lot bigger than neon. Sodium has its valence electron in the next higher principal quantum number orbital. It is much larger. And now we're in that, I guess, third row of the periodic table. The valence electrons, sodium has an effective nuclear charge of +1. And as we go across the row that starts with sodium, the effective nuclear charge increases, +2, +3, +4, as we go all the way across to the noble gas, and it gets smaller and smaller again. We're getting a lot of S's today, eh? Give me one sec. Okay, let's see if that gets rid of some of them. Okay, so now we're at argon, and then we move up to krypton, and our valence electron is now in the 4s orbital, and we can see it decreases. And then 5s1 and 6s1. As we get bigger, we have a huge increase in atomic radius. Let's go back to potassium, that 4s1. As we go across the periodic table from potassium, it gets smaller and smaller. And then we see something funky happening around manganese. If you look on your periodic table, what block of the periodic table is manganese in? Go ahead and just shout it out. D. Remember how we said the D region, when we're outside of the main group, we can have some funky stuff happening. The effective nuclear charge is calculated differently as we move through the transition metals. The shielding ability of those d orbitals is different than the s and the p. So as we go across, the shielding changes and we have some funny increases and decreases in size. But the general trend continues across. So here we're in the D block, the transition metals. And then we go up to rubidium, 5s1. And then as we go across, we hit some funny business in the transition metals and the intertransition metals, I believe, as well. So it gets a lot more exciting. Oh, the intertransition metals are the next one as we go across. We're looking for the big patterns. As we go down, they get larger. As we go across, they get smaller. We can recognize there are some funny anomalies on a variety of different reasons. We don't need to memorize all the anomalies here, but we know they happen as we move through the transition metals and inner transition metals. But we need to know the big trends and why. Okay, very related to atomic size is bond length. The same idea, the same underlying foundation for this trend applies. We can talk about atomic radii, and you know that word from grade 2 math class? That's from the center of the circle to the outside. That's the radii. Well, if we want bond length, it's the distance between the two atoms, those two nuclei. So if we measure the distance between the two atoms, we have the bond length. And as you would probably expect, as we go from fluorine all the way down to iodine, or iodine, the bond length is increasing. Why? Well, we just have larger atoms. Their valence electrons are in larger orbitals. Those electrons are hanging out further and further away from the nucleus. I like to imagine this as little kids giving each other a hug. If you try to measure the distance between their two hearts or their two chests, tiny little toddlers, it's like this close. But if you had like two big bodybuilders trying to hug each other, the distance between their two hearts is a whole lot larger just because they're bigger people. Same with atoms. Larger atoms tend to have larger bond lengths because they're bigger. Okay, so I would like you to take 1 minute, chat with the person beside you, and see how many patterns you can find in this table. You do not need to memorize this table, but there are many important patterns. Chat with the person beside you. What patterns can you observe? And 3, 2, and 1. Okay, so I've circled the pattern we just talked about on the previous slide. As we go down the halogen group, those bond lengths increase in size. Hands up who found at least one other pattern, 2 other patterns, 3 other patterns, 4. There's at least about that number. There are a lot of patterns as we go across. Let's see if we can find another one. Carbon, nitrogen, oxygen, fluorine. As we go across our periodic table, see how the bond length gets smaller. Because as we go across a period, the effective nuclear charge increases and those atomic sizes decrease. That's when both of the atoms were changing size. What about carbon, nitrogen, oxygen, fluorine? Again, if you look on your periodic table, we're going across a period as we do that. But this time they're all bonded to hydrogen. Well, hydrogen is staying, its atom is the same size, but the bond length, we can see, decreases. Why? Well, carbon, nitrogen, oxygen, fluorine, they're getting smaller in size. As we go down the periodic table, we saw fluorine all the way to iodine. Those get bigger. Well, fluorine, chlorine, bromine, hydrogen, as we go down the periodic table, in that same halogen group, all bonded to hydrogen, we can see the atomic radius getting bigger, or not the atomic radius, the bond length increasing as we go down. Okay, so I-clicker question. Chat with the person beside you. This is the same table. What pattern do you observe related to bond order? And bond order, as a reminder, is a way of talking if it's 1 for a single bond, 2 for a double bond, 3 for a triple bond. So chat with the person beside you and submit your answer. And 10 more seconds. And 3, 2, and 1. Okay, most people went for B. Excellent. Part of this question was having you identify the pattern. Part of this question was also having you interpret these answers. So the way that they're phrased, sometimes it says decreasing, sometimes it says increasing. As this increases, this decreases. paying attention to the phrasing is also going to help you here. Okay, so well done. Bond length decreases as bond order increases. Where do we see that? Well, if we're looking at carbon-carbon bonds, we can see the bond length decreases even as the bond order increases. We know that triple bonds are stronger than double bonds, which are stronger than single bonds. More electrons in those bonds pull those two nuclei together. So the triple bond is even shorter and tighter. And we see this pattern when we're looking at oxygen single to double and nitrogen single to, make that go the right way. Large to small, single, double, triple is pulling in. So we can see many patterns happening here with bond length as we go across the periodic table, down the periodic table, and as we change the strength of that bond from single to double to triple. Okay, so we've been looking at atoms so far that are neutral, but we now need to add to the discussion when we're working with ions. What happens to the size of that ion when it goes from neutral to charged? So let's start here with sodium. Sodium has 11 protons, and if it's neutral, it has 11 electrons. Its electron configuration is the noble gas neon plus an electron in a 3s orbital. That is sodium neutral all by itself. It has an atomic radii of 86 picometers. Do you need to memorize that number? No. But do you need to know and predict? If you know 186, you could predict if the next one is going to be higher or lower depending on what we do or how we compare it. Well, if we take away that valence electron, we're still going to have 11 protons, but now we only have 10 electrons. The electron configuration matches neon, but we no longer have a valence electron in the 3s orbital. Now all the electrons are in 2s and 2p orbitals. So we're not using the larger orbitals, we're using the smaller ones. Makes sense that the cation, the positively charged ion, would be smaller. And we now have more protons than electrons. So there are fewer electrons being pulled in. If you look at the radius change, it's almost half the radius change. If you calculate area, pi r squared, you can see, I don't remember, it's like a quarter of the size or even smaller. It is way smaller when we go from neutral atom to the cation that has lost 1 electron. Why? Well, we're using different orbitals and we have a different proton to electron change ratio. Same thing applies to cesium. We go down our periodic table, we can see cesium is bigger than sodium. We take an electron away from cesium to make cesium plus. Yeah, it got a whole lot smaller. And we can see the pattern is maintained as we go down the periodic table. If we're comparing +1 sodium to +1 cesium, it's going to have a similar atomic radius, or ionic radius now, compared to the neutral atoms. Okay, so cations are always smaller than their related atoms. Well, let's see what happens when we go the other way. Let's take a look at chlorine now. It has 17 protons. If it's neutral, 17 electrons. Well, if we now add an electron to make chloride, the size of that ion increases dramatically. We can see the radius has almost doubled in size, which has a multi-factor impact on the volume and the overall size of this 3D ion. We now, in the chloride ion, we still have 17 protons, but now we have 18 electrons. We have even more electrons compared to the protons, so it's harder to hold those all in. As well, we also have electron repulsion happening in these valence electrons. They're kind of pushing away from one another, which is making this even larger. Anions are always larger than their neutral atoms. Why? Well, we've added an electron, sometimes to higher principal quantum numbers. Here that wasn't the case. It was still in the same, whatever, p orbitals. But we have a greater electron to proton ratio. We have more electron repulsion between these valence electrons. So continuing on with our ions, these are two principles here that you definitely want to know, and hopefully they make intuitive sense. Like it would make sense as you add or remove electrons, they would get larger or smaller. We definitely need to know those trends. And there are two more trends that you need to know when we compare, to just give you a full toolkit. Next item to know is that for the same element, if we have a +2 charged cation compared to a +1 charged cation, the dication is going to be much smaller than the monocation. If you take 2 electrons away, that's going to be way smaller than just taking 1 electron away. So here's my atom. You took 1 electron away, it got smaller a lot. That's just what we talked about. The cation is always smaller. But if you take 2 electrons away, it's going to get even smaller, much, much smaller. Doubly charged cations are always smaller than singly charged cations. As well, dianions, like a 2 negative charge, is always going to be much larger than a monoanion. We have an atom, has its atomic radius. We add an electron to it, boom, drastic increase in size. You come along and you add a second electron, so now we have 2 more electrons than the number of protons, even larger. So dianions, it just exacerbates the problem, even larger. Okay, so for the same element, that trend will always hold true. And finally, for isoelectronic species, what does that mean again? We talked about this term already. Who remembers this term? Thumbs up. Okay, awesome. That means they have the same electron configuration, the same number of electrons in the same orbitals. If we have an isoelectronic species, same number of electrons in the same orbitals, well, whichever one is the most negative is going to be big, and the most positive is going to be small. Let's see why that makes sense. Here I have fluoride, neon, and a sodium cation. All of these species have the noble gas electron configuration of neon. All of these have 10 electrons in the same orbitals. They have different sizes because their electron to proton ratio is different. Fluoride has 9 protons, neon 10, and sodium 11 protons. The same 10 electrons are being pulled in by 9 protons, or 10 protons, or 11 protons. If we have 2 more protons than electrons, or 1 more proton than an electron, it's going to pull it in even tighter. We have more cations pulling those electrons in. So if we have an isoelectronic species, we can predict, based on that series, which species is the largest and which is the smallest. Okay, so let's get to this example here. We want to arrange the following species in order of decreasing radii. That means large to small, from largest to smallest. We need to explain our rationale, and these are the 4 species that we need to compare. This problem, I think, is the most challenging problem in this topic. This problem is asking you to make comparisons between 4 different species. It's easier to make comparisons between 2 species. But when you're comparing 4, that's a lot of cognitive load. This type of problem, I wouldn't want to just do in my head. I don't think I could do that confidently. If I need to make multiple comparisons, I definitely want to write these out. So I'm going to ask you to chat with the person beside you for 1 or 2 minutes. I've paired up some of these species. I want you to decide, as with your people around you, which of these species in the pairs is bigger. Then use your greater than or less than sign, the alligator mouth eating the larger species. Which is bigger, which is smaller for these pairs? Chat with the person beside you and explain your rationale. Explain why. And 3, 2, and 1. Okay, who would like to explain their rationale for the first comparison? H negative to helium. How can we make that determination? Which one is bigger? Thank you.
So we know anions are larger than the neutral atoms. So because H minus is an anion, we can say that it's bigger than He.
Very close, thank you. Anions are bigger than their neutral atom. That is true. But here I have a hydrogen and I have a helium. So that rule doesn't necessarily apply because they're different atoms. But you are correct that anions are bigger than their own neutral atom. That is true. What else can help us figure this out? What other rule that we talked about?
There's more protons in hydrogen than helium.
There we go. That is also true. We can see helium has 2 protons pulling in those 2 electrons. Meanwhile, hydrogen only has 1 proton pulling in those 2 electrons. The proton to electron ratio is different. That is true. That can help us identify this. What's the name for that rule? What type of series do we have here in the first comparison? Anybody want to guess? They're not the same atom. Super. Do you want to say that just a bit louder?
Isoelectric.
Oh, and you know what? My microphone just died. Isoelectronic, and that is correct. Because they have the same number of electrons but different protons, these species are isoelectronic. Helium has 2 protons pulling in 2 electrons. Hydrogen only has 1 proton pulling in those 2 electrons. Therefore, helium is going to be smaller. Okay, what about the next one? Helium to helium plus. Anybody want to shout that one out? And I'm not going to take the time to change the batteries. Just go ahead and say it nice and loud.
The helium, the neutral one, because it has a greater effective nuclear charge.
Okay, great. Helium has a greater effective nuclear charge.
Oh wait, no. Helium plus is a greater nuclear charge because it has 1 less electron. The helium has less effective nuclear charge, so the radius is bigger.
There we go. Helium to helium plus, they're the same atom. They have the same number of protons, but the number of electrons is different. If we're comparing the same species, but the charge is different, then the cation is always smaller than the neutral element because of that proton to electron ratio. Well done. Okay, He plus to H plus. This one's a little bit trickier potentially because normally as we go across the periodic table, the elements get smaller. And then if we have the cation to anions, normally that applies. But that rule doesn't apply here as we go across the periodic table. Does anyone have an idea of why? As we're going across the periodic table, it doesn't actually get smaller. Yes. Do you want to just say it nice and loud?
Okay. They're both lacking one electron, but He has one orbital while H plus doesn't have any orbitals, so He plus would be greater.
Excellent. There you go. That is the answer. H plus doesn't even have any electrons. Here we only have a nucleus. It doesn't even have an electron orbital. It's just the nucleus. So H plus is always going to be the smallest of anything that you can likely come up with unless it's something else that doesn't have any electrons. Okay, and the last one, I'll do this one here. We have the same species, hydrogen to hydrogen, but the anion is definitely going to be bigger than the cation. Okay, this was a big question. We were asked to order these species from largest to smallest. Another way of saying that is according to decreasing radii. So we'll leave this up on one screen. Which of the following is correct? How can we arrange these species according to decreasing radii? Chat with the person beside you. And 10 more seconds. And 3, 2, and 1. Okay, and large majority going for E. We have chatted about the rationale for each of these comparisons that leads us to the final answer. Making all these comparisons on the top of our head would be very challenging because there are multiple reasons for these different comparisons. If you have a question like this, take it by pairs, take it piece by piece, explain the rationale, and you too can solve atomic radii. Okay, we're moving on to our next trend. So far we've talked about atomic size or atomic radius. We've applied it to anions and cations, and we know how to see the trend across the periodic table. And 3, 2, and 1. Thank you. Okay, the next important trend that we need to identify is ionization energy. We call this IE for short. It's very important to know the definition of this term so that you can compare it to the other definitions we're going to talk about later today and next class. So what is ionization energy? Well, it's the energy that we need to put in, the energy required to remove a valence electron from a gas phase species, so an atom or an ion. Each of the parts of this definition are important. Here, we're stealing away, we're removing an electron, which is in contrast to other trends. So we're stealing an electron, we're stealing a valence electron, one of the outer ones that we can grab most easily. And it's very important that this is in a gas phase atom or ion. If it was in a solid crystal lattice, the numbers would be very different. Because we're not just removing an electron, we have to worry about intermolecular forces and a lot more factors. So in a liquid, we have intermolecular forces. In a gas, we don't have to worry about intermolecular forces and attractions between molecules. So here we want an atom or ion all by itself. It's in a gas, and we want to steal one of the electrons. We can write it out in a formula, starting with the neutral atom. And then on the product side, it means we've come along and we've stolen an electron. That species, once it loses an electron, becomes positive. We could do this twice. We could then come to the A+ that's just lost an electron and steal another electron as well. And that would be called the second ionization energy, or the second step. We'll come back to why in just a minute. Here on the table, we have a whole bunch of numbers. So 520, 900, and so on. These numbers are an indication of the energy required to remove an electron from that atom or ion, or 1 mole of those atoms or ions. Let's look down the periodic table. I'm going to skip hydrogen, or actually no, I'm including hydrogen for sure. As we go down the periodic table, from hydrogen, 1312, lithium, sodium, as we go down, we can see these ionization energy values are decreasing. What does that mean? Well, it's easier to steal an electron from cesium compared to lithium. Now, why is that the case? Here, as we go down the periodic table, the amount of energy required to steal an electron gets smaller. Let's imagine that I am a lithium atom, and I have 1 valence electron in a 2s orbital. I'm really tiny, and so I'm holding this electron in a 2s orbital nice and close to me. Meanwhile, cesium has more electrons in S and P and D and F, and cesium is so big compared to lithium. Its electron is like way out here. So if I come along and try to steal an electron from cesium, its electron is so far from the nucleus, it's like, sure, you can just grab it off, why not? Compared to poor little lithium holding it nice and tight and close. Based on the atomic radius, as the size increases, those electrons are further and further and further away from the nucleus. It's easier to just steal an electron away. So that's why the ionization energy decreases as you go down the periodic table. Now let's look at the big trend as we go across the periodic table. Let's look at potassium to calcium, arsenic, bromine, krypton. As we go across the periodic table, the big trend that we see is that you have to put in more and more energy to steal an electron away. Let's start with potassium. It has its 1 valence electron. It has, I don't know how many protons because it's not on my periodic table there, however many it has. As we go across, we know the effective nuclear charge is increasing. Those electrons are being held more tightly with a stronger effective nuclear charge, and the atomic radius is decreasing. So even though we're adding electrons, we're also adding protons as we go across the periodic table, the effective nuclear charge is increasing. By the time we get over to bromine, those electrons, even though they have more electrons, are being held so tightly and so closely, you're going to have to work a whole lot harder to steal an electron from bromine. Imagine a little kid with a lollipop. Yay, I have my lollipop. And then kids who just love their lollipops so much and are holding them so close to their chest. It's easier to steal if it's kind of out over here versus way over here. And again, as we go down the periodic table, someone who's like, yay, this is my lollipop, versus someone who has so many lollipops they don't even care if you steal one away. I see a question. Go ahead.
Is this also related to effective nuclear charge?
Is this related to effective nuclear charge? Yes. Because as we go across the periodic table, effective nuclear charge is increasing. Those valence electrons are being held even more tightly and close with a stronger attraction to the nucleus. So yeah, you're gonna have to work a lot harder to steal that away. I'm not gonna invite someone up, but you can imagine I'm holding my electrons out here versus like here. You're gonna have to work a lot harder to steal those away from me. Okay, so that's the big trend. But as we move in closer, same slide, there are a few anomalies. And these are some anomalies that we need to know. And you know what? I'm going to back up for 1 second, because before I get to the anomalies, I need to go back to first and second ionization energy. Imagine a kid with its valence electron. Maybe it has 2. And you come along and steal one away. It becomes an anion, A+, and you've stolen its electron. Can you imagine how tightly it's going to hold to that remaining electron? That second ionization energy, the energy required to steal a second electron after you've already chosen one, is always going to be much larger. Because the proton to electron ratio has changed, those electrons are being held much, much tighter. So second ionization energies are always much greater than the first. Okay, those are the big trends, but there are some exceptions. Although those are the big trends, let's imagine we plot this out here. I'm going to say 520. Here's my little y-axis. There's 520. Here's 900. We've gotten bigger. That follows the trend. But then we go down to 800. That was actually a decrease going across the periodic table. That doesn't match my big trend. From boron to carbon, 800 to 1,000. That increases. Carbon to nitrogen. Yep, that increases. Ooh, nitrogen to oxygen has gone down just a little bit. That's an anomaly. It's breaking our big trend. From oxygen to fluorine, we can see it increases. Fluorine to neon, it increases. When I draw this out, I can see beryllium to boron is an anomaly. Although the big trend, it increases as we go across, that trend is broken there. Nitrogen to oxygen, as we go across, it actually decreased just a little bit as well. I'd like you to think about that. Write out the electron configurations from those atoms and see if you can come up with a reason as to why we have these anomalies, because this is where we'll pick up next class. Have a great day, and I will see you on Friday.